In the last video, we have used the bash script to perform a parameter sweep to reproduce figure 4b of the manuscript and gone through the parameter list in the input file MCTDHX.inp. In this video, we will reproduce the results in figure 5a and explain the parameter list in the input file for analysis. So first we will show figure 5a. So this is figure 5a. It shows the one-body correlations between 5 bosons in the ground state in a double well potential with barrier height equals to 20. The difficulty in the simulation of this figure is that there exist some excited states with energies very close to that of the ground state. These excited states, however, have extremely different particle correlations than the ground state. The relaxation can thus be easily trapped in the excited state and cannot reach the proper ground state. Such excited states occur when the number of bosons and fermions is odd. To circumvent this problem, we will do the same simulation multiple times, each time with a different randomly generated initial condition. We then choose from these results the one with the lowest energy as the ground state. So first, we would go to the folder related to this simulation, which is in relax10 prop 16 fig 5ae and in the subfolder relax. Here we see that there are 3 files, 2 input files for the simulation and for the analysis respectively, and 1 bash script for the purpose of running multiple times and then comparing the energies. So as we can see in this bash script, it essentially creates 10 folders and copy the input file inside the folders. Here it copies the executables and then it runs the MCTDH-X. Next, here it takes the last line of the nopr.out file from the simulations, and then it takes the last entry from these files. So as we can see from the manual, in the nopr.out file, the last entry in each row is the energy of the state. So essentially, we are taking the energy of the simulation results. So, and in the next step, we are comparing this energy with the energies from the previous results, and in this way, we can determine the state with the lowest energy. And in the end, we remove all other non-ground states or the excited states and retain only this ground state. And we call this folder as the ground state folder. And this is what the bash script is doing. For the purpose of a better illustration, I now create a simpler version of the bash script. It is done in here, the parameter sweep.sh. In this bash script, we simply create 10 folders, copy the input file inside the coders and the executables, and then we run the simulations and the analysis. And in this bash script, we are not comparing the energies, and we will compare the energies manually later. And here we have the analysis.inp and input file.inp. And the input file for the simulations. Now let's first look at the input file, MCTDHX.inp. We are simulating bosons. The number of bosons is 5, and we are simulating with 8 orbitals. And importantly, for the purpose of illustration, we choose barrier height equals to 13 instead of 20 because the effect of this excited state is more obvious when the barrier height is 13. Next, we want to look at this analysis, this input file for the analysis, analysis.inp. A detailed description of this input file can also be found on this manual. It can be found in the input of the analysis program. So here we have this name, the name list for the input variables. In our case, we want to, because we are doing the simulations for 20 time units, we want to specify the starting time and the stopping time of the analysis, both of which are 20, and the time point is equals to 1. Next, we want to specify that we want to do the analysis to generate the density distribution in the real space, and also the density distribution in the momentum space, and also the correlation functions in the real space. More importantly, this dilation here, it specifies the resolution in the momentum space, and in our case we choose dilation equals to 10. Now that we have prepared everything, we now run the simulations parameter sweep.sh. After waiting for some time, we have finally finished our simulations. So you can see that there are 10 files, test 1 to test 10. These are 10 relaxation results generated by the bash script parameter sweep.sh. And now we want to look at the results from these 10 relaxations. And as usual, first we want to look at the nopr.out file from each simulations, and specifically we want to look at the energies from this result. And because we are simulating with m equals to 8 orbitals, so the energy is in the 10th column. So this is the dependence of the energy on the imaginary time. And as you can see, the energy drops pretty fast at the beginning, and then it converges after some time. However, in such a large scale, this result is not so informative. So we want to look at the result after it converges, which is in the last 10 time units. Now we replot it, and we can see that the 10 different relaxations converge to 4 different states. So the green one is the ground state, then the blue and purple ones are the first and second excited states, and then the yellow one is the third excited state, which has a pretty high energy compared to these two. Furthermore, we can see that the energy difference between these states, for example, the ground state and the excited state, is pretty small. It is roughly 0.005, and if you compare it with, for example, the trapping frequency, which is equal to 1, this energy difference is really small. Besides the energy, we also want to look at the orbital occupation. This is shown in the 9th column. This is the occupation of the first orbital. So you can see that, for example, this one, the green one, if you remember, it is the ground state, and then the blue one is the first excited state, purple is the second, and then the yellow one is the state with pretty high energy. And so you can see that the occupation of the first orbital is very, very different from state to state. This indicates that in these simulation results, the particle correlations are also very, very different. So this can be confirmed by looking at, for example, the density distribution in the momentum space and also the one-body correlation functions. And to do this, first we want to look at the figure out which state is which. And to do this, we can look at the last line of the NOPR file from each simulation. And after comparing these results, we could figure out that, for example, test 7 is one of the ground state, and test 6 is the excited state, the first excited state, and test 9 is the second excited state, and then the test 5 is the third excited state. And so now we first plot the density distribution in the momentum space. So this is from the ground state and from the first excited state. And this is from the second excited state. So you can see that, for example, the purple one is the ground state, is the momentum distribution of the ground state, and there is only one peak. This indicates that the correlation between the two wells are almost vanishing, and the two wells are not insulating from each other. However, if you look at the excited states, for example, the first and second excited states, you can see that besides this central peak, there are also two peaks surrounding here. These two peaks indicate that the correlation between the two wells is still pretty large, and therefore the two wells are not insulating from each others. To confirm this, we can also look at the one-body correlation function, for example, in the ground state. So this is the one-body correlation of in the ground state, and you can see that the correlation between the two wells are roughly 0.2, so which is rather small if you see the results for example, in the excited state, you can see that in the first excited state, you can see that this correlation is almost reaching 0.6, and also in the second excited state, the correlation between the two wells are also 0.6, so which is pretty large. So therefore, we can see that the particle correlations are indeed very different between the ground state and the excited state, although they have a very slight energy difference. In the last part of this video, we will look at figure 5e. So this figure, it shows the one-body correlation function between the two wells as a function of barrier height of the double well in a system of 5 bosons. And specifically, we want to focus on the ground state property, which is represented by the blue line here. The tricky part in the simulations is that there are again excited states with energy close to the ground state, and the relaxations can then be easily trapped in the excited states. A straightforward way to circumvent this problem is to do 10 different simulations at each barrier height, and then compare the energy of the resulting states. This method is, however, time-consuming. We therefore try to use a cleverer way. We generate the 2 different many-body states, one with high correlation between the 2 wells and one with vanishing correlation between the 2 wells. Then, we use these 2 many-body states as initial states respectively to do a parameter sweep. After that, at each barrier height, we obtain 2 many-body states with probably very different particle correlations. We can therefore compare the energies of these 2 states and decide which is the ground state. In this way, we can save our time by doing only 2 relaxations instead of 10 at each barrier height. The folder for this figure is given in by the folder Relax Series Fig 5e. And as you can see, there are 2 subfolders, Relax Series 1 and Relax Series 2, and they are responsible for different initial conditions. And you can see that the structure of these 2 folders are exactly the same. We have an input file for the simulation, an input file for the analysis, and 3 binary files for the initial condition. And in the first subfolder here, we have the many-body states with vanishing correlations between the 2 wells, and in the second folder here, we have the many-body states with finite correlations between the 2 wells. And these binary files are generated using a relaxation, of course, and this relaxation lasts for a time unit equals to 10. Now we can look at the input file of the simulation. As we can see here, the initial state is chosen as guess equals to binary files. So which means that we want to read from the binary files for the initial state, and we choose to read from the time unit equals to 10 from the binary files, because we have done the relaxations with time equals to 10. So now by running these 2 parameter sweep bash script, we are able to run the 2 parameter sweeps inside these 2 subfolders and obtain a result. And then we can compare this result to figure out which one is the ground state at each barrier height. And I'm not going to do these simulations. So in this video, we have seen how we can circumvent the low-lying excited states and tell the ground states from these low-lying excited states. So we do this by doing the simulations multiple times and choosing from all these results the one with the lowest energy. In the next video, I will show you the whole procedure of doing an MCTDH-X simulations. I will start from scratch, modifying the input files, and I will also do the whole procedure, including the relaxation, propagations, and analysis.